So today nothing is working. Hello, welcome back to a new video, to all of 6 of you who are my friends basically, so thank you for tolerating me, guys. I also want to thank you, Andre, for letting me know that I was pronouncing matrices the wrong way. I still get confused sometimes about it and say matrices. I had a professor who said matrices, so it stuck with me, but I will try to say it the right way, so thank you. And let's start with today's video, which is about matrix multiplication and its properties. Let's start. I didn't consider the right space for it, so I'm just gonna stay like that. Sorry. I would like to start with the scalar multiplication, just because we've seen something like that in the case of the opposite matrix. So in that case we used as a scalar -1 because we wanted to find the opposite matrix and have all its entries with the opposite sign. So I'm gonna write something down now. We have that in scalar multiplication, given a matrix A, we can write it like this, where K is a scalar, a number. So in the opposite matrix case, K was -1, and that was when we had -1 multiplied by A, and all the entries of A at the opposite sign. But the general case would be that K can be any number, and that means that we are multiplying every single entry of A for this number. So let's give an example. So in this case, for example, we have that K is equal to 3. I just chose 3. It doesn't have any particular meaning. It could be any number, any even negative number. So we have K equal to 3, and A, it's a 3 by 3 matrix, and this is it. So in this case we have that 3, I'm gonna write it down here, can you see? Yeah, 3 by A is equal to, we just multiply every single entry for it. 3 by 1, 3 by 3, 3 by 2, 3 by 5. So this is our K, which multiplies every single entry. And our solution, I'm gonna write it up here. 3 by 1, 3, 9. I got so mad at technology. Anyway, what I was saying is, I just finished computing this thing. Anyway, I was filming and then I realized that everything shut down, so I was not filming and I was talking alone in my room. Yeah. we can now start with the actual matrix multiplication, and since I'm lazy, I'm just gonna wipe this off. It's green. Green. Okay. Matrix. Perfect. So at this point, to be able to multiply matrices, we have to follow one very important rule, which is you can multiply two matrices if and only if, this is like, I think you will find this thing right here in many papers, like math papers or anything related. So if and only if, which means that this condition is necessary to be able to multiply two matrices. And so what I was saying is we can multiply two matrices if and only if, let's write this down, the number of columns of the first matrix is equal to the number of rows of the second matrix. And in this case, it's gonna be very useful, the fact that we've already seen how to define the dimension of a matrix, if it's a matrix 3 by 2 or 4 by 4 or anything, because that's how we're gonna see both if we are able to multiply the matrices, and we're gonna also see the final dimension of the solution. Let's see how. That A belongs to M, M, N. This, I think I said this before, this is the set of all infinite, because there is an infinite number of these matrices. So infinite of all infinite matrices M by N. Let's now take B, which belongs to M, N, L. Let's say L. This is the set of all infinite matrices which have dimension N by L. So, in this case, we can already say two things. The first thing is, this is the number of columns of A. This is the number of rows of B. These two are equal, so we already know that we can multiply these two matrices. The second thing that we can see already, without knowing what the matrix looks like, we can already see that this M by L will be the dimension of the solution of this multiplication. So let's give an example. Actually, I decided to do something else before that, which would be write the formula that gives us every single entry of the matrix. So we will call a generic entry of the matrix Cij, as I think we've already used this in the sum of matrices. I think so. Anyway, in this case we have the summation that goes from r equal to 1 to n. N is the number of columns of the first matrix and the number of rows of the second matrix. I know that it's quite difficult to relate these formulas to what we see when we are actually writing a matrix. But in this case, it's really important to just think about the formula. So we know that matrices start from a number of rows and columns that is equal or greater than 1. If it's equal, we are talking about vectors. If it's greater, we have matrices. And then we are going to, in this case, we are going to sum a formula that I will write here for each and every number of row and column. So we go up till n. N is the maximum value, the maximum number that we can go up to in a number of these summations. It's interesting to see that this is the index. How do you say in English? Index, I think. This is the index that moves. So this is, oopsie, that's the index that will move from 1 to n.